Well, let's talk about human population. So we talked about carrying capacity. Well, let's instead of looking at other animal populations, let's look at ourselves because the reality is most of the stress that our planet is feeling right now, environmentally, is a consequence of human population. So if we're going to try to help the world survive us, we have to learn how to control our own size of our population. So let's just get on it. So, for most of humanity's existence on this planet, we've lived as hunter gatherers that had very little impact on the environment. We lived in small roving bands. We looked to find food. We basically did not alter our environment in any significant way. Oh, that was a weird little glitch. Okay, um, and so we didn't cause the environment of our planet to be particularly hurt. But that all changed about 12,000 years ago, because about 12,000 years ago, people being smart made this discovery. Hey, I went out and gathered these grains, but now I see them growing outside my cave. Hmm. Instead of going out and gathering them, why not just let them grow right here? In fact, why don't I just make it better for them to grow here and find ways of making them grow even better and trying to select variants of this that are even better. So basically, agriculture was discovered about 12,000 years ago, and here's what happened. First of all, people immediately began to significantly alter their environment. Let's chop down these trees. Let's drain this area. Let's plow this land. And by doing this, we and let's plant a monoculture. So we completely transform the landscape in order to accommodate this croplands. Now, if you're going to grow crops, you're going to have all this food you want to store. So you're basically investing a lot of energy growing these crops, unlike when you're just wandering around finding it. And now you're going to want to protect it. So we built cities to protect them. So now we have the birth of urban areas and the different environmental factors that go along with urban areas, like waste management and so on. And the other thing that happened is that human population significantly increased because more food, more resource always means a larger population. And sure enough, let's just look at what happened. Now, you got to take this with a little bit of skepticism, but basically, we don't really know how big populations were. But basically, what we see is, at different times in the past, there have been different increases in human population, but a really big one occurred about 10,000 years ago, a little after 10,000 years ago, when people discovered agriculture. And it made a significant change in the amount of humans on this planet. So let's take a look at this. About, say, 8,000, 9,000 years ago, people discovered you can plant things and they'll grow. You don't have to go hunting for them anymore. Well, then what happens is a few thousand years go by and people go, wait a second, my plants aren't doing very well, but what if I dug a ditch and brought in some water? And this soil's kind of not the best for growing plants, but what if I found a way of like churning it up with a plow? And so basically plowing and irrigation has made a sudden huge increase in the amount of food that was available. And what we see is after that, there was another big increase in the number of humans on this planet, but we're talking significantly under a billion people. Now, should point out the plague, a lot of times people think like diseases are going to have a big impact, but actually, remember, a disease is, at least in the case of a one off like the plague or COVID, that's basically a density independent thing, environmental pressure. And so what happens is it just drops the population temporarily and then it comes right back up. Now, what happened though was around 1800, in the mid 1800s at least, people, we call it the Industrial Revolution, people discovered how to use fossil fuels to do work for us. We made steam engines and then internal combustion engines, and that changed everything. It brought in industrialized plowing, industrialized water pumping. It allowed us to move things from one place to another, large distances, to support people who weren't near the crops. It allowed us to refrigerate things to support people who weren't near the crops. And it basically led to the greatest explosion of a life form on this planet, and it hasn't stopped yet. Let's just take a look at where we are. It's kind of scary when you look at these graphs, because basically, ever since the Industrial Revolution, we have been on this screaming upwards exponential growth curve. And the thing is, from what we said before, this is not supportable. It can't go on forever. Eventually, there are going to be density dependent factors that are going to suppress the growth of human population. And we're going to reach either a carrying capacity, or worse yet, we might overshoot it and have a dieback. And that's something that's got a lot of people concerned for a couple centuries now. No one really knows what's going to happen in the future, but let's just look at three situations. One is nothing. We don't do anything. We just go for it. And the human population continues to scream upwards. And good golly, by the end of this century, we could be up around 16 billion people on the planet. They probably can't support that many people. Now, another one is that we look at as countries become developed, the birth rates tend to drop off, the growth rate tends to drop off, and it tends to flatten the curve, so to speak, to use a COVID term. Or maybe we could be fairly assertive and aggressive about this and purposeful about this, in which case we could probably reduce human population from not much higher than it is right now and bring it back down in your lifetime. This is certainly something that is achievable and probably a good goal to have, and something we'll address in our next show. Now, the first person to bring this to the world's attention was this guy named T.R. Malthus back in the late 1700s, and he basically was an economist. And here's what he said: he said, "Look, the rate at which that we are able to make resources available to people grows in a linear fashion. We year after year we develop more and more land, but it grows in a linear fashion. But population grows at an exponential rate. And so what you find is over time you're going to eventually have to reach this point of crisis, he called it, a Malthusian catastrophe, a point at which human population exceeds the resources we have to feed them. This is basically before people knew about carrying capacity. Basically, what we're talking about is overshoot and die off. And he said, like, when this happens, there's going to be war, famine, disease. It's going to be terrible. And he's got a point. And this is something that we still don't know if it's in our future or not. We certainly don't want this to happen. And there's things we can do to prevent it from happening if we're purposeful about this. Now, it's important to keep in mind that most environmental problems are in one way or another linked to the size of the human population. So let's just go through some of these. More people means we have to have more agricultural area to feed them, which means we have more deforestation, more loss of habitat, more loss of species, more loss of soil, increased runoff, all these things because we have to feed more people. There's going to be more water consumption, which means there's going to be basically water as a resource we'll talk about later in the year. We're going to run out of it faster. Increased energy production, like people want electricity. People need power. So that means we're going to have to burn more coal or do somehow access more energy to support all these extra people. And these people, in order to supply them with resources, we're going to end up having manufacturing pollution and human waste as a result of that. So all of this happens as a consequence of human population. Reducing human population, or certainly limiting its growth, is of vital importance to our planet. Now, one of the best things we could do is slow it down and reverse it. But in order to do that, we have to understand how and why it grows. So let's get on it. Okay, there are four things that determine growth rate. And that is the rate at which babies are born. That's the birth rate. How many are born? By the way, these are usually done by year. These are annualized. So we have how many babies are born in a country each year. How many people die in a country each year. The death rate. How many people move into a country? The immigration rate. How many people leave a country each year? That would be the immigration rate. Now, these are the only four things that are going to control the population of a country. Now, immigration and immigration don't matter for the planet as a whole. So we could, if we want, just limit our conversations, we will for the most part, just to birth rates and death rates. Now, birth rate, and you are expected to be able to calculate this, is calculated by basically just taking the total number of live births, how many babies are born, survive being born, and divided by the population. Usually we say at mid-year, because if we're going to annualize it, what it is at the beginning, what is it, then take the midpoint, okay? We won't beat that issue too much, but it's worth keeping that one in mind. So let's just use this as an example. So we have a population of 45 million people, and we record 1,350,000 births. What's the birth rate? We just take the number of births, 1,350,000, divided by the population at mid-year, 45 million. We get 0.03. Now, that's expressed as a decimal. Often we want to express things as a percentage, so we just multiply that by 100. So we say, well, we have a 3% birth rate in this country. Right? Now, the thing is, we often use a measure called crude birth rate, just to make things a little bit more complicated for you. People don't like to have small numbers, and growth rates can, even when turned into a percentage, can still be less than 1. And people don't like working with numbers less than 1. So what demographers often use is what's known as a crude birth rate. And that's all that really means is take that same calculation we just did, live births divided by the population at mid-year, and simply multiply it by 1,000. So what we're saying is, like, how many births per 1,000 people were there? So using the same thing as before, if we did this here, instead of saying 0.03, if we multiply that by 1,000, what we get is 30. So we'd say the crude birth rate for that country is 30 births per 1,000 people. That would be called what we call the CBR, the crude birth rate. Now, the death rate is the same idea, except we just do it with how many people die each year. So we divide the total number of people who die each year by the population at mid-year. We get the same thing. And we could also express it as a crude death rate by saying how many deaths were there per thousands of people in the population. Now, by comparing these two things, we can come up with the growth rate. Now, it's worth noting that if the sorry for scratching me, that's gross. If the birth rate is greater than the death rate, the population is going to go up. And that's what we see here. And if the death rate is greater than the birth rate, the population is going to go down over time. And if the birth rate equals the death rate, it's going to be constant. And so let's just look at this idea of growth rate. We call it the rate of natural increase. So the rate of natural increase, although it could be decrease, and that's starting to happen in some countries actually, but for the most part in human history, it's been an increase. The rate of natural increase is said to be just take the birth rate minus the death rate. You could do it as a crude birth rate and crude death rate, or just a birth rate and a death rate. So, for example, in 2017, the United States had a crude birth rate of 11.8 children born per thousand people, and a crude death rate of 8.6 people died per thousand people. And so that gives us a natural increase of simply birth rate minus death rate. That gives us 3.2. That means in that year, 2017, we added 3.2 people to the population for every 1,000 individuals. Again, we divide that by 1,000. We could express that as a decimal percentage, or we could express it as take this and multiply it by 100, and that would just be a standard percentage. But as I said, see how it's less than 1. People just don't like that. That's why we often use the crude birth rates and crude death rates. Now, another thing we often like to use is doubling time. How long is it going to take for a population to double? And by the way, this rule I'm about to teach you works for investments as well. So if you want to make a lot of money, listen up. So it's called the rule of 70, and you will be tested on this, both in my class and on the test in May. Okay, so basically, here's how you find the doubling time. The doubling time is simply equal to 70, always the number 70. If you want to know why, ask your math teacher, like I would know. And then divide it by the growth rate expressed as a percentage. Okay, not CBR or crude growth rate, but as a decimal percentage. What percent growth? Okay, so not as a decimal, not as 0.03, or not how many people per. You'd say 3%, not 30 people per thousand or 0.03. It's got to be as a percentage. So let's just look at how this works. Okay, so for instance, Pakistan has a growth rate of 2.1%. How long is it going to take for the population of Pakistan to double, assuming nothing changes? Okay, we just use the rule of 70. We say the doubling time is equal to 70 over the percentage growth rate. So 70 divided by 2.1, that gives us 33.3 years until it doubles. Or if you told me the doubling time, I could tell you what the percent growth rate is. Another thing you should be able to do is you should be able to look at a graph like this and figure out the doubling time by looking at the graph and then using that to come up with the growth rate. So let's just try this. So if I want to figure out what the growth rate of this country is, what I would do is I would try to establish how long it took it to double. So if you look here, we should find the doubling time is about 40 years. So if I start at 20, and we're going by fives here, so that's 10, 20, 30. After 40 years, the population went from 20 to 40. It doubled. So 40 years. Let's try again. Let's start from 30 and see how long it takes to double to 60. So here's 30. So we're at here. So we go 10, 20, 30. After 40 years, we doubled to 60. So it seems like it's about 40 years. So I'd say, well, the doubling time is equal to 70 over the percent growth. The doubling time is 40. So therefore, I would say the percent growth rate is going to be 70 divided by 40, which gives you 1.75% growth rate. Now, we can also, if we want, account for immigration and immigration, and you should be prepared to do that. That's helpful when we're looking at individual countries, which is really, yeah, I mean, it's important. Okay, so let's just look at it here. Okay, so basically, there's two things that increase the population. birth rate and immigration. So I take those two things and I add them together, and I subtract from them the sum of the two things that reduces the population, death rate and immigration. So basically, the rate of growth is equal to birth plus immigration minus death plus immigration. So let's just run through an example. So for every 1,000 people in a country, 32 births, 15 deaths. Remember, this is crude values here. 8 people moved in and 4 people left. What is the percent growth rate? So I simply say, all right, I had 32 births, 8 people moved in. That's immigration. That goes here. All right. So that gives me 40 minus. Now I had 15 people die and 4 people left. So 15 plus 4, that'd be 19. So then I would say 40 minus 19, 21. So that means the crude growth rate of this country is 21 per thousand, 21 people per thousand individuals expressed as a percentage. I would say 21 divided by 1,000 gives me a decimal percent, 0.021. And if I multiply that by 100, I get a standard percent of 2.1% growth rate. Oops. What just happened there? Okay. I can't see what's underneath here, but I think yeah, it says, so if I come with a negative value here, if this number here was bigger than this one, it would just indicate the population was decreasing at a certain percent. Okay. And here's another example. I'll let you do it. You don't need me to read it to you. You can look at it at your leisure. But basically, I simply take the number of births plus the number of people who moved in. I take away the number of people who died, and I add to that the number of people who left, and I divide that by the total population at mid-year, and I get this decimal number. I could express that as a crude value by multiplying it by 1,000 and say 16.7 people per 1,000, or I could multiply it by 100 and express it as a percent. I could say it has a 1.67% growth rate. And it's worth noting that when we look at a graph, here's what we'll see. If we're curving upwards, we have a positive growth rate. That basically means that births plus immigration is greater than deaths plus immigration. Now, the smaller the value gets, the less upward it slopes. And when I finally get to here where it's flat, that means that the two are equal to each other, that there's just as many births as deaths, or like I say, births plus immigration equals deaths plus immigration. And if it's negative, I'll see it start to go down. So that those are the factors for calculating populations and why populations matter. Sorry if this lasted too long, but these are big ones. You will definitely get a lot of these on your test.